Let's talk about a problem that every single one of us has run into. That moment your project starts to get so complex, it feels like it's collapsing under its own weight. But what if the fix wasn't about writing more code or better code, but about changing how we see our code in the first place? Let's get into it.
You know how it goes. You build something cool, maybe a tool to scan thousands of Maven repos to build out a giant dependency graph. And hey, it works, but it is painfully slow. So the obvious first thought is, okay, I'll just throw some concurrency at it, speed it up. And that's usually where the real nightmare begins.
Because all of a sudden, your nice, clean logic is just a mess. It's a tangle of thread pools and boilerplate and configs that are impossible to keep track of. It's brittle, it's hard to change, it's hard to even understand. But what if we're digging in the wrong place for a solution? What if the answer is actually in those architecture diagrams we draw, before we even write a single line of code?
So here's how we're going to break this down. First, we'll look at that code complexity trap we all fall into. Then, we'll get into this wild idea of diagrams that actually run. We'll unpack what it means to think in nodes and connections and see how these things called processors bring it all to life. And then, we're going to circle all the way back and solve our original concurrency problem visually. And by the end, you'll see how this could be a whole new way to build.
All right, so let's start with the problem. The thing we all know so well. The code complexity trap. It's that sinking feeling you get when you try to add one simple feature and it just breaks everything. You've opened a Pandora's box of side effects and complications you never saw coming.
So here's the real-world example we're working with. The goal was simple enough. Scan a bunch of repositories, map out all their dependencies. The first version, single-threaded, got the job done eventually. The obvious fix? Adding concurrency. Sure, it made it faster, but the cost was huge. The code got rigid, totally bloated with configuration files, and it became a real headache for the team to work on. I'm sure that sounds familiar.
Okay, problem established. We get it. It's a mess. Now, let's talk about the solution, and it is a major paradigm shift. What if those diagrams we draw on a whiteboard to explain our logic weren't just static pictures? This is the big idea right here. Imagine this. Instead of drawing a diagram and then trying your best to write code that kind of, sort of matches it, what if the diagram was the application? I mean, literally. An executable computational graph where the thing you see on the screen is exactly what gets run. No more drift between the plan and the reality.
Now, to really wrap our heads around how this even works, we need to shift our thinking a little bit. We need to start thinking in graphs. And don't worry, it's a beautifully simple idea, and it all boils down to two fundamental building blocks.
So what is a graph? Well, at its heart, it's just a way of organizing things. You've got your objects, we'll call them nodes, and then you have the relationships between them, which we'll call connections. That's it. It's kind of like a mind map, Each idea is a node, and the lines you draw show how they relate to each other. It's an incredibly flexible way to model pretty much anything. Okay, let's drill down a bit. A node can be whatever you need it to be. It could be a single letter in a word, a user in your database, a whole complex object. It's just a thing. The connection, though, that's what gives it meaning. It's a directional link, basically an arrow, that says this thing is related to that thing in this very specific way. That simple combo is all you need to build some amazingly complex and meaningful structures.
And this is where it gets really cool. We can stack layers of meaning on top of each other. So take Hello World. At the most basic level, we can make a graph connecting each character to the next one. But then we can build another layer on top, grouping those characters into nodes that represent whole words. Then maybe another layer, a dictionary, that connects those words to definitions and counts how many times they appear. And why stop there? We can add a semantic layer that connects hello to similar words like hi. And just like that, you've built this rich, multi-layered, and super meaningful data structure, visual.
Okay, so we've got our data all structured up in this nice graph of nodes and connections. That's great, but it's still just a static picture, right? How do we make it, do something? How does it actually run? Well, this is where the magic comes in. This is where we talk about processors.
The best way to think about it is like a three-layer cake. The bottom layer is just your raw data, numbers, text, whatever. The middle layer is the graph itself, the nodes and connections that give that data structure and relationships. And then the top layer, the icing on the cake, that's the processors. These are little bits of logic that you attach to the nodes and connections to make them actually perform actions. To really make this click, let's use a few metaphors. My absolute favorite is the printed circuit board, the PCB. Just picture it. The graph is the green circuit board, the nodes are the empty sockets on that board, and the processors are the little computer chips you plug into those sockets to give it functionality. The connections? They're just the copper traces on the board connecting everything together. It's such a great way to picture how you can just plug and play different bits of logic to build a working system. All right, let's bring this all the way back home. Remember our slow Maven dependency scanner? We wanted to add concurrency, but we didn't want the horrible complex code that usually comes with it. Well, with this graph-based approach, the solution is, well, it's just beautiful.
So sticking with that circuit board metaphor, the fix is unbelievably elegant. You just create a special type of connection processor. This one is called an async invocable connection processor, and you just place it on the connection between two nodes. That's it. This little processor acts exactly like a capacitor in a circuit. Its only job is to get a task, hand it off to a new thread, and then pass the result along.
And this right here, this is the big aha moment. Look at the difference. In the old way, concurrency is buried deep inside complex code, hidden configs, tons of boilerplate. But with an executable diagram, it becomes a simple visual component. You can literally see where the parallelism is happening, and you can tweak the thread pool size right there on the connection itself. In terms of clarity and just being able to maintain your own code, this is a massive leap forward.
Now, this is obviously more than just a clever trick to solve one specific problem. When you start to adopt this way of thinking in graphs, it has some really profound implications for how we can build and manage software, especially at a large scale. And listen, this isn't just a fun thought experiment. The team behind this is using it in the real world to manage over 415,000 lines of code spread across 31 different repositories. This is a battle-tested method for taming some serious real-world complexity. So what's the big payoff here? What do you actually get? Well, for one, you can actually manage huge, complex code bases because you're navigating a visual graph, not getting lost in a sea of files. Two, your team becomes way more efficient because the architecture diagram is the code. There's no room for misinterpretation. And three, and this is the really exciting part, it's a way to future-proof our jobs. We humans can focus on the big picture, high-level graph thinking, and let AI get better and better at just generating the code for the low-level processors. In the end, it all comes down to this one simple, incredibly powerful idea. When your diagrams can actually run, what you see is what you get. The design and the reality are finally one and the same. It's a game-changing concept. So I'll just leave you with this question to think about. When we move away from thinking in straight linear lines of text and start thinking in these dynamic, nonlinear graphs, we open up a whole new world of possibilities. So if you could really build with diagrams like this, what's that one complex problem you've always wanted to solve that you could finally visualize and conquer?